Yeah. Yeah, I have to go home because it is past 7. That is the dual tensor. That is when you have A mu nu is a tensor, it is anti-symmetric. Then you can make a different tensor out of that, rho sigma. Maybe I should write it like that, rho sigma mu nu. And by definition, this is called the dual tensor, a rho sigma. And I think we usually put a half in front of it. And by definition, this is what we call the dual tensor, usually in physics. In mathematics, this is called the Hodge star operation. Just a different name for dual tensor. But it is actually very simple. It is just, you have this 4x4 matrix and you multiply them by a bunch of minus signs and then you get this one. It is physically important. Physically, it corresponds to interchanging the electric field and the magnetic field and putting a minus sign in front of the magnetic field. So it is important. But physics, magnetic fields are not completely the same as electric fields. They're almost the same, but we don't have magnetic monopoles, whereas we have electric charges. So it is very different. They have very different properties, magnetic and electric fields. So again, this has the Hodge star, or this. It has important physical applications.
So you defined pseudo-invariant over there, and here you say that the multiplication of the dual tensor by A is a pseudo-scalar. Does it have a similar definition? Or?
Yes, pseudo-scalar. That means if you transform this according to Lorentz transformation, because we have here, if we look at, say, A rho sigma star times A rho sigma, and A rho sigma star, so that is given by that. So this is equal to 1/2 epsilon rho sigma mu nu times A mu nu times A rho sigma, if I write it out. And if you now do Lorentz transformation, we have to Lorentz transform everything. It is actually not invariant because of this factor. There's an extra factor determinant of L. So it is only, that is why it is not a scalar, it's a pseudo-scalar. It's exactly because of that determinant, if you write out the Lorentz transformations.
All right.
And in physics, we do have pseudo-scalars. They happen in physics. And it's a very important quantity, FF dual, F mu nu, F mu nu. This quantity has been discussed many times in this room by people working on their problems.
So generally, just what is the difference between a pseudo-scalar and an actual scalar?
A scalar, if it transforms on the Lorentz transformations, it stays the same. So if you would have A mu nu, this is invariant. If I apply a Lorentz transformation to both of them, it just drops out. It is exactly the same. So the prime one is A mu nu, A mu nu. Yeah, I wrote down the indices like that. A mu nu is identical if I do. When I Lorentz transform this one, I get an extra factor determinant of Lorentz transformations. So it is not invariant.
So what I'm getting is that it's simply multiplied by a scalar when you apply the Lorentz transformation?
Yeah.
Okay.
Yeah. by a +1 or -1, depending on the determinant of Lorentz transformations.
I see. So that's pretty good. Oh, so here you define the relation with, I'm not sure exactly what to call the epsilon symbol. I know there's a more formal name, but I just can't remember it right now.
That is the epsilon symbol. This one.
Right.
And there are some relations when, like this one, epsilon mu nu rho sigma times say epsilon mu nu and here alpha beta. So there's a sum over mu nu. So because these are all these are the same and they have to be all different. So in order to be non-vanishing, either rho must be equal to beta and sigma or equal to alpha, or rho must be equal to alpha and sigma equal to beta. I think I said twice the same. So this must be equal to delta rho alpha, delta sigma beta, and the other term is equal to rho beta delta sigma alpha. Because when this actually corresponds to just interchanging these two, that gives a minus sign. That means there must be a relative minus sign. And I can then calculate one of them. For example, if I choose this 2, 3, and I choose this 2, 3, then I only have this term, but they're summed over. So how many terms are in this sum that are non-zero?
So how many, okay, so they're non-zero when all of them are different. So they're zero when mu and nu are the same, and we're summing mu and nu from 0 to 3. So I'm pretty sure.
But I took this already 2 and 3. That is fixed.
Oh, right. So we're just summing them over 0 and 1?
Yeah.
All right. So then for 0, 0 and 1, 1, they're 0. And for 0, 1 and 1, 0, they're 1, right?
Yeah.
Okay.
So we have a half here. And I hope I have that 2 here in my notes. Oh, sorry, not 1/2. There's a 2 actually, because there are 2 possibilities.
Okay.
Because we sum over 2, and so this is a very useful identity, which if you work in problems that involve this tensor, you often have to use that.
It may just be bad memory, but I don't think you referenced delta before this page. So what exactly is delta?
Delta is the so-called Kronecker delta. It is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j.
Okay.
It's a very useful thing, and used all the time. In matrix form, delta is just the identity matrix, and 0 otherwise. So we use it all the time in physics and also in combinatorics.
All right. I can see a little bit of why this is true now. So, so how do you come about this identity in particular?
This one?
Yes. If they share one indices, then they're
Yeah.
equal to.
So the second one is when there are 3 indices equal. So that is epsilon mu, doesn't matter, mu rho sigma and epsilon alpha nu rho sigma. And now we know, because these three are equal, this must be equal to a delta mu alpha with some factor. We also know that if we choose this, we can choose it anything. So we choose this 0 and that 0. Then this can be only 1, 2, 3. And it can be any of them. You sum over all possible 1, 2, 3. So how many combinations you can have?
All possible 1, 2, 3, 6, right?
Indeed, 6. So it is 6 times the delta. And I wrote...
There's an extraneous minus.
Why did I write minus? There should be no minus. There should be no minus. So it is plus 6. Right. So that's a typo.
And that explains the other identity too.
The last identity, yeah. If you sum over all of them, then and this is also equal to that. So there are 4 more things. So then it becomes 24. So if you have epsilon nu rho sigma, epsilon nu rho sigma, that is equal to 24.
All right. That was so. Right. This is where I really started to.
Integration.
Yeah.
Yeah. That is a. I don't know if you know Gauss theorem.
In physics?
No, mathematics. I don't think so. Gauss theorem is when you have integral of a divergence, that is d mu, in fact in 3 dimensions, dkak over a volume. You can write as integral over the area, so that's for volume, and then you integrate over the surface of the volume of ak times nk, that's the normal, and it's a surface integral, dA. So you have some arbitrary volume. It goes here, and maybe this is dashed. So it's an arbitrary volume. You integrate this A, that's a vector that depends on the position, and it has indices. And then the surface is here. There's a normal vector. That's a unit vector perpendicular to the surface. And the statement is that these two are equal. That is a Gauss theorem.
No, that was definitely not in the scope of my class.
No. You typically learn that. I don't know. Third-year students here learn that, I think. So I'm pretty sure you didn't have that. And this theorem we actually can extend to 4 dimensions. In when this runs for relativity, this is a 4-dimensional integral, and these indices run from 0 to 3.
Oh.
And then again, it becomes a more complicated thing, which you have to work out. And I gave an example here. I even don't remember it exactly. So it gets complicated. We don't directly need it. It is just an example that you can do that when we need it. But if you don't know this theorem, it is very important for electrodynamics, for Gauss law. That is a relation. to find the total charge inside. So in electrodynamics, you have the equation divergence of E is 4 pi rho. This is charge density, and this is the electric field. The divergence is dxk of ek. You know the Gauss law?
I've seen it, but I can't remember it right now.
Yeah, and so you use this term. So divergence E. Did this then, if we use that is equal to 4 pi rho, and the integral over the charge density, that is equal to the charge. So this side, when I integrate it, is a charge in the volume. This side is, I have here, this is now the electric field times n dot dA. So this is the electric field in the radial direction. So it is everywhere the same. If there's only one charge inside the sphere, it is everywhere the same. And this is just the area. It is 4 pi r squared. And this is charge density, that is E times Q. So what you find is that this is the same, that E is equal to Q divided by r squared. So you find the Coulomb's law from the Gauss law. And that is why it is important. We always work, you may have learned the electric field with 1 over 4 pi epsilon 0. And we always put that equal to 1.
Right, K. So.
K, we don't have, K is 1, which you can do if you use so-called Gaussian units. But again, this theorem, if you didn't have that, there's a whole set of other things. And so the question is, because the next few pages are on electrodynamics, so the question is what you want to do. Because there are things like electrodynamics, you don't really need that for general relativity. And if you spend too much time on that, we cannot cover, we cover less of general relativity. So the question is what you want to do. If you just follow my lecture notes, in class, the reason I do that in class is because it is part of the material. That's part of the course description. That is why I have to cover it. If I would teach a course only on general relativity, I would not cover the electrodynamics. That is, P is Q dot, and P is Q dot, and P dot is equal to minus dH dQ.
I feel like we're using different notation here. Yeah, I think
okay, let's give an example. The Hamiltonian is 1/2 mv squared. And I can write this as p squared divided by 2n.
Oh, the p represents momentum, actually. Sorry. And q represents force.
So this is just kinetic energy. So P is, and this is Q dot squared, say mq dot squared divided by 2. So the momentum is, okay, so I did set it wrong. P is equal to dH dq dot, the derivative of the Hamiltonian with respect to q dot. And if I differentiate this, it becomes m times q dot, the mass times the velocity. P dot is dH dq, there's no Q dependence, so that's equal to 0. And indeed, this is the energy for a free particle that has only velocity, so the momentum doesn't change. So it stays at a constant velocity. If there's a potential, there's also a potential energy, V of Q, then this is not equal to 0. Then there's an extra term that is minus dV dQ. And this is the force. So the change in momentum is equal to the force.
I see.
So these are Hamiltonian equations of motion. And for the Lagrangian, you have it is equal to the kinetic energy minus the potential energy. The Hamiltonian is the kinetic energy plus the potential energy. You can also write down equations of motion for the Lagrangian. And then you actually do it in a different way. You define the action. The action is integral L, and L is a function of Q and Q dot times dt. And you integrate between some, say, initial time. It doesn't matter at this moment where you integrate. The important thing is that you look at, so you have here Q of t, some trajectory, so there's an initial one time and this is the final time. Let's say all trajectories are the same. And what you do is you look at the change in S if you change, this is Q of t and this is Q of t plus delta Q of t. If you change the trajectory a little bit, you are going to change the action. So this is then going to L times Q plus delta Q, Q dot plus delta Q dot dt. And then I Taylor expand this. So this is L Q, Q dot plus delta Q times dL dQ plus delta Q dot dL. Delta Q dot times dL dQ dot. So I Taylor expand this to first order. And when I integrate that, so this is S plus delta S. The first term becomes S. Then I have here integral delta Q dL dQ times dt. And then the second one is integral dL dQ dot times delta Q dot times dt. What I want is, I want to have the variation outside everywhere. But here I have a derivative. So I integrate this by parts. So that then I get a minus sign. I get here d dt. You know how integration by parts works. Delta L, the derivative with respect to Q dot times delta Q times dt. And there are no boundary terms because I chose them all equal. So delta Q at the endpoint is equal to 0. So what you see is now, what I now say, and that's the variational principle, that the equations of motion are given by delta S is equal to 0. So this must be equal to 0. When is this all equal to 0 for all variations? That is the case when the coefficient vanishes. So this means that dL dQ minus d dt dL dQ dot is equal to 0. If this is the case, this action vanishes, this variation vanishes for all variations in delta Q. And these equations are known as the Euler-Lagrange equations. They are very important. And if you look again at this example, what is dLdq? dLdq is minus dVdq. So dLdq is minus dVdq. And dLdq dot, q dot is only the kinetic energy, so that is mq dot squared divided by 2. So dLdq dot is 2q dot divided by 2 is m times q dot. And here we have minus ddt times dLdq. Q dot was m times q dot. And this is equal to 0. And what you see, what we are getting is m times q dot. So what we are getting is m times q dot dot is equal to minus dv dq, which are again the correct equations of motion. So this is the force and this is the acceleration. So m times a is equal to, and that follows from a very simple equations of motion. These are the equations of motion. So it's a variational principle. And this is also important of physics, that in classical mechanics you can derive all equations by using this variational principle.
Right, so the Euler-Lagrange equation, which basically determines motion, just follows from delta S equals 0?
Yeah.
Okay.
And this actually has a very deep reason. And it has to do with quantum mechanics. Because in quantum mechanics, if you want to find the amplitude to go from q equal to t to q equal to 0, it is given by e to the power, is given by, I will explain this, by e to the power I h bar times dx. It's is divided by h bar. And h bar is a constant of nature. It's very small. So and s is the same action as that. And this gives the correct quantum expression. And I integrate here over all possible trajectories, over all possible paths. They don't have to be differentiable. So I integrate over all possible paths, and this gives the correct quantum result. If I now take h bar going to 0, because there's an I here, that means this is going up and down, you can write it as cosines and sines. And if this h is very, very small, it basically all cancels out. Only the smoothest trajectory remains. And that is exactly the trajectory with this property, with no variation. So that means that the classical mechanics are the ones you get when h bar is going to 0. And that's indeed the correct classical limit of quantum mechanics. And that is why this works. But the amazing thing is that this was discovered well before quantum mechanics by Euler and Lagrange.
I don't think I'll put too much effort into understanding the reason as much, but...
No, there are textbooks behind this. Yeah. So and we mentioned the action for we can. Did you look at that already?
Page 21?
Yeah.
A little bit. I just want to first ask, what do we need action for here?
The action.
What are we trying to do with action?
What we want to do is to write the equation of motion in relativity. We know that equations of motion has to be the same for all observers. And that is why the action must be a Lorentz invariant. So when we have only one particle, we have very few invariants. So when we have a free particle, so we have x mu, these are the coordinates. When we have a free particle, we only know one invariant. So the only invariant is s squared, is x 0 squared minus x squared. The action must be invariant. So the action must be integral ds. That is what s should be.
Can't argue with that.
So it's invariant, and you might wonder maybe we should times a constant. So this is invariant, and then we want, so this should give the classical equations of motion of a free particle. Free particle is a particle that just goes at constant velocity. That's what this should give.
Why do we have to add alpha?
Because it should be dimensionally correct. And we don't know it yet. Because for any constant, this also would be invariant. For example, this could be the mass of the particle. It actually turns out to be m times c. Mass times the speed of light.
Oh, so...
And you do that by actually deriving the equations of motion from this one, by doing what I did here, a variational principle. And so you derive the equations of motion, and you want them that in the classical limit, when the velocity is much less than the speed of light, that it reduces to these ones. So that the kinetic energy is mv squared. And the amazing thing, if you do that, is that you also find a potential energy. And a potential energy is mc squared. So that is the energy that is inside mass.
It seems like that conclusion is made in 3 steps over here. There's definitely something that's being skipped here, right?
Not. Yeah, no, not really. We can do it. And so we know that the action is alpha times integral ds is alpha times integral ds dt times dt, and s squared, s is equal to the square root of x 0 squared minus x squared. This was s. So, and ds is the square root of dx0 squared minus dx squared. So ds divided by cdt, that is dx0, is the square root of, here there's 1 minus dx, and here we have then c dt squared.
I just realized why you have to put alpha. It gets a little confusing when you have 2 s's, because the space-time integral and the accents start looking a little bit of the same, and I thought that was...
Okay,
yeah.
so this capital S.
Yeah, I thought that was saying s equals alpha s, and I was starting to get a little confused.
Okay, yeah.
I see.
Okay, so we know what ds dt is. So what we have is that the action is alpha times, here we have ds dt. that is the integral times c times the square root of 1 minus v squared. And now we can expand this, so this alpha times integral c, we expand this in a Taylor series. That is 1 minus, do I have here? I have here a c squared. V squared over, should be dimensionless. V squared over 2c squared. And so what this is integral alpha times c, that's the first term, minus alpha times v squared divided by 2c squared and multiplied by a c. But we know from this limit that the Lagrangian, that's this thing, that should be equal to the kinetic energy minus the potential energy. So this is like v squared. So this should be equal to the kinetic energy, that is 1/2 mv squared, and this should be equal to the potential energy. So 1/2 mv squared. So that means that if you choose alpha equal to m, then you get that. And there's no c in it. So alpha is, and there's a minus sign, so alpha is equal to minus mc. If you put that, we get exactly 1/2 mv squared. And if you look at this term, you see that it is it is plus, it is t minus v. So this should be equal to minus sign. It was t minus v. And the potential energy is alpha times c, so it is equal to alpha times c, it is m times c squared. And that's the famous result of Einstein, that mass is equivalent to energy. And the formula is...
That it's this way around now, because this is t and this is v.
T minus, oh, you're right, thank you. So this is kinetic energy and this T minus V. So this is actually minus V. That's what you're saying. Yeah, that's right. So this is equal to, it actually doesn't matter because I determined alpha. So alpha was not yet determined. If you do it in this way, then you find here a plus and you find that alpha is equal to minus mc. And you find this again the same.
All right.
And that's already an important result, that for a free particle, the action is given by m times c times ds. And I think, what did I acted this minus mc. You're right. So s is equal to minus mc times the integral of ds. And from varying this, you get the relativistic equations of motion. So you don't have to think, just do it, and then you get the right result, because this is invariant.
Okay. So that's just the equation of motion that...
Now, this is the action. And from the Lagrangian equations, you get the equations of motion. The Lagrangian equations are still valid because they follow from quantum mechanics. And quantum mechanics is still valid in relativity. It's a very good theory. It is even valid in when the speed is near the speed of light.